Hello, welcome to the Big Bang. My name is Kapolina, and today we'll be continuing learning more about muscle mechanics. Last time we learned about the force-length relationships in muscles, and we will be building on that knowledge to talk about muscle force-velocity relationships. In the last video, we learned that the force generated depends on the number of cross bridges the sarcomere makes. It takes a certain amount of time for the cross bridge to form. As the load decreases, the muscle will move faster. As the muscle moves faster, the sarcomeres have less time to form cross bridges, which means that the output muscle force will decrease. On the other hand, as the load increases, the muscle will move slower. As the muscle moves slower, the sarcomeres have more time to form cross bridges, which means that the output muscle force will increase. The velocity-force relationship can be used to develop the relationship between power and velocity. Power is calculated by multiplying force times velocity. When power is plotted against velocity, it could be seen the maximum power corresponds to optimal muscle shortening speed. When force over velocity is small, the power output will be small as well. Before we combine everything we have learned, we need to mention activation energy and how it relates. The higher the activation force, the higher the normalized velocity and length will be. Now, let's combine everything that we have learned about muscle mechanics so far into one equation. In order to find the muscle fiber force, you need to factor in the force at zero velocity, activation, the force from the active force length curve, the active force from the force velocity curve, and the passive force from the force length curve. Let's try to simplify the equations for the following four conditions. When the muscle fibers are isometric, the length of the muscle is constant, and because the length is constant, the active force velocity is zero. As a result, the active force from the force velocity curve goes to 1, and the equation simplifies as seen on the screen. What about when the fiber is at its optimal length? At optimal length, the muscle is outputting its maximum force, so the active force is at its maximum and the passive force is at its minimum. The active force from the force length curve becomes 1 and the passive force becomes 0, so the equation simplifies as seen on the screen. When the fiber is maximally activated, the coefficient for activation energy becomes 1, and the equation simplifies as seen on the screen. Our last case is the passive case. The passive case is the opposite of the optimal fiber length, since the active force is at its minimum and the passive force is at its maximum. The active force from the force length curve becomes 0, meanwhile the passive force becomes 1. The equation simplifies as seen on the screen. Next time we'll be covering the Hill-type model and its parameters. I hope that this video is helpful, and thank you for joining us. I will see you next time.